You saw the pitch, you joined the room, and we hope you're here for this discussion. I'm without actually any further precursors. I'm just going to wait just a few minutes for everybody to join, but we have a half an hour to discuss this topic. I'm just astonished, given the I'll tip our hands and say it was a last-minute organization of all this stuff, how much on time this whole thing has been. So we'll try to do that. Welcome to the Composable Computing Panel. Composing is the ability to map or allocate resources to tasks, compute nodes, hardware, generally speaking. And the idea has been around a while. I think it's one of those things that goes in cycle. Are we converging or disaggregating? Are we composing or what are we doing? So hopefully we'll explore that here. I didn't really get enough time in the intro to let the panelists introduce themselves, so I'll do that in just a minute. You tell us just a bit about yourself and why you're interested. And then I've prepared a set of 5 questions, which I hope will needle you guys into saying something interesting. If I fail, then please say something interesting anyway. So let's see. Why don't we start with Maria?
Good evening, everyone. I'm so glad to be here. My name is Maria Ruiz Varela. You can just call me Maria. That's fine. I am an HPC engineer, formerly with Intel, where I was responsible for RAS validation for the Aurora supercomputer. Right now, I am in the job market, actually, and very thrilled to be joining this panel.
Thanks, Maria. So James Cuff, I technically retired, seemingly to fail miserably at it. Spent a whole bunch of time at fancy universities building HPC systems. I have an unrequiting love of new and interesting technologies, and so I remember talking with Jeff Layton about PLX switching, and that, if only we could just plug stuff into the PCI bus, get rid of the network drivers, magic could happen. And that was, 15 or so years ago. And I think we're starting to see some chinks of daylight in this technology. It all comes down to the management on the switches, comes down to software. And so I also know, just in terms of watching other center directors struggle with their delivery of computing, there's never enough memory, the storage is too far away, you can't stuff enough GPUs in a box, and it's just ew. And so I'm kind of here to play both kind of devil's advocate, pro, and kind of con. Thanks, Alan.
Alan Benjamin, you want to introduce yourself?
Sure. So I'm Alan Benjamin, and I am the CEO at a company called GigaIO Networks, where we are trying to do what James just talked about, right? In terms of being able to use PCI switches today, and in the future, it will also include CXL, to be able to compose resources. And a trick that we have now is we can route across PCI, so we can also run things like MPI natively across the network. And it's really thrilling to watch, this come together and deliver a capability. And as James probably would have continued, with each time we give capabilities, we also find it creates other sorts of problems. And, boxes can get awful hot with lots and lots of GPUs. And so things like thermals and power and, the ability of putting all these resources and controlling them become a challenge. But it is really an interesting fantastic place to be in.
Great. So we're going to try to also stay on time. And so I've got 5 questions here. And let's try to keep to a total of about 5 minutes per question. So let's think back, it wasn't so long ago that we were building blade servers and, I mentioned shared memory machines. This idea of composable architecture, is generally an idea that relies on flexibility. So my question is this: composable architecture disaggregates and broadens the limits to connection between computing, memory, I/O, and storage components. Is this just building a bigger computer with more of these on a given bus or interconnect, or is there more to the idea than that? James, let's start with you.
Jumping up and down. I think the bigger idea is that it's actually probably about smaller machines and more focused compute. This isn't, in my point of view, it's not a race for a top 500 composable machine. There's a whole different set of class of problems that I think both Doug and Don spoke to just in the introduction about sometimes doing the wrong thing. Certainly in research space, you never know what shape these things are. We did not expect cryo-electron microscopy to be the computing busting algorithm that it turned out to be. And so any tool or technique that you can do tight coupling with, a northbound integrator or a software stack that can enable sort of TCP-like flexibility, but with like a bit more performance and not as messy as MPI, that seems kind of cool. But the devil's in the details. Maria?
Thank you, James. I think a bigger computer would add more of the same building blocks. In this case, it would be the blade, which is the compute node. So there is more to the idea than that, definitely. In a disaggregated system, you group resources in pools, a pool of GPU, a pool of FPGAs, a pool of NICs, perhaps memory, which I think right now it's you cannot compose DRAM directly. You need to emulate storage class memory, like obtain as DRAM and present it to the application as DRAM, but it's slower. It's not it. But the idea is to disaggregate the devices, the very expensive devices, and create pools of each of one of them. So it's not just creating a bigger computer. And as James was mentioning, we have a fabric to interconnect all of those pools, which is done through PCIe switches. So this is interesting because that means the CPU GPU ratio is not fixed as it would be in a traditional system, in a compute node that we know right now. This means that we can have more finer grain access to resources, not just the compute blade level. And I think that's very exciting. I was talking about this with someone just a few days ago, and I was telling him, this sounds like playing with Legos, and I love that. And he's like, you got it.
That's great.
Yeah. So
yeah. So and with CXL.memory coming down the road very soon with memory. So I'll throw it to Alan then. Are we just building a bigger computer with more components on a given bus or interconnect, or is there more to it than that?
Well, it can be groups of computers too, by the way. Right. So it's not necessarily creating a individual server with a bunch of stuff in it. Right. At the end of the day, we always say, if your job will run inside of a server today, people don't need composability because they have it. Right. But what happens is they have more storage or more acceleration or different kinds of acceleration. And it's really about flexibility, not necessarily size. So in some cases, it can be small. It can be quite small. It could be 2 or 3 servers and a handful of GPUs, or it could actually be quite large. It could be hundreds or even thousands of CPUs and storage. And
So let's pick up on that if we could.
Go ahead.
It ties really closely to my next question. And you mentioned it can be small. So let's keep in mind that as currently implementing in shipping products or products that are being discussed, we're talking more or less about PCIe buses extending past single machines, right? So how closely is this current state of composable infrastructure tied to the use of PCIe as the choice of interconnect?
Are we doing the same route round?
Well, let's go in reverse. I'll throw it back to Alan.
Okay. So to some degree, it depends upon what it is you are composing. So if you start, to use Maria's terms of Lego devices, if you start with the slow Lego, start with, storage media, you can actually compose pretty well across Ethernet or InfiniBand. Doesn't have to be PCI. As you go up in terms of performance of the device, then you need things with lower latency and higher bandwidth. And so PCI tends to be a good choice to be able to do that. But, and when we get to memory, there's things that we can do across PCI Express today with memory, and we show people that, and that surprises them. But to really get memory to be effectively composed, CXL is going to do a lot of things for that. But so I guess the answer here is it doesn't have to be PCI, but it does depend upon what it is you're trying to compose. And if you're trying to do things faster than storage, then it does need to be PCI today.
Yeah, and if part of the idea is to lower costs by not having to have, let's say, an InfiniBand or OmniPath interconnect, that's a consideration as well. So James, how closely is composable infrastructure tied to the use of PCIe, or do you just agree?
I mean, yeah, clearly, but I just want to play my kind of academic devil's advocate on this. It's clear there's still a lot of work to be done, right? I want to sort of kind of level set. You mentioned sort of shipping product and so forth, and I think companies like Alan's need to be congratulated, working with the National Science Foundation, SDSC at one end of the country, MGH-PCC at the other. Forgive me, I forget where the lower one was.
And TAC that's bought both of the major companies, right? So,
right. And those test beds and the work that you are doing, Alan, too, are going to be crucial to shake this out. Because when you start having a memory mapped fabric moving at high speed with all of the weird stuff that goes on inside of, clustered computing, you shake out a lot of bugs and there's also a lot changing on that backplane that, CXL and so forth are totally different software and engineering. And you start then having to worry about the length of bits of copper, right?
So. Absolutely. I'll have a question about that in a little bit. Maria, anything to add or?
Yeah, as far as I understand, PCIe 4 it's what's being used now. That's what we have. Then down the roadmap, we will have PCIe 5, and then, perhaps in a 2-3 years time, CXL. I believe you still can compose racks that are connected over PCIe and then use Ethernet to go farther, because right now, it won't be as performant because, if you don't have the option of using an optical cable, which is the one you could use to reach 100 meters distance, if you don't want to afford the cost, if you cannot afford that, then Ethernet could be a choice, an alternative.
Great. Yeah, it's music to the ears of someone who spent years building grids. All right, so let's try to go in the next couple of questions a little further beyond the current state of the art of PCIe 3 and 4 in these shipping products. PCIe speeds have been doubling each generation, and the latest generations, as James hinted, have required tricky signal interpolation. If you sit down and study the PCIe 5 specs, as a physicist, it's just horrifying to me what they're expecting people to do. They just, it requires PCIe 5 generation 5 already requires advanced dielectric materials to be used in motherboards and interface cards, and there could be restrictions to the physical distances that signals can safely travel. So will this result in limits to the physical size of deployments in composable infrastructures that use PCIe 5, and even we'll ask about further generations later, and therefore maybe require the use of larger numbers of transceivers? Will that drive up complexity and cost? What's the roadmap staying within the PCIe, immediate future of PCIe 5?
Alan, do you want to take the techie part of it? Because I'm not an electronics engineer, but I know you've got a whole bunch of them.
Yeah.
And Dan Hurst is already asking about PCIe 5 and 6 in the chat. Is that okay?
PCIe 5 is going to hurt some people, says Dan, and PCIe 6 is an abomination. So it's easy for a spec committee to write things, but there is some reality. We have processors announced, both Sapphire Rapids and Genoa announced as supporting PCIe 5. We already have NVIDIA with an announced product line for HDR 400 that will be based on PCIe 5. People will be building things. My question is, as these speeds go up, does that create a practical limit to building PCIe switches with extended distances?
That was my comment for Alan. He's that side of my screen. I guess being the CEO of a company that builds this stuff might keep him up at night. I don't know.
Yeah. Okay, Alan, you want to take this?
I'm with this. Can you hear me?
Yeah.
Yes.
Yep.
PCIe 5 is going to be I agree from a physics and device standpoint. It's going to be really fascinating to see. The cable guys tell us, by the way, that they are absolutely convinced we'll get PCIe 5 to run even across copper cabling, which sort of blows my mind. And we'll probably get out to 2 meters, maybe even 3 meters on copper cables, and out to 100 meters on fiber. So it is mind-blowing that you can move the things at the speed and that they say. Proof's in the pudding. We haven't seen them yet, but we know they're there. We're fully confident that they will deliver them.
Thanks, Alan. I just saw a question from Mike Sherman too about expectation of composable blocks working with mix and match between vendors. And that's the sort of the classic piece, isn't it? That as we add more complexity, the hardware keeps getting faster and faster. Our engineering and electronics engineering have to become more and more sophisticated to keep up. And then all of a sudden, we then want to start sharing all of these slightly kind of ratified standards. And I was tweeting earlier and giving a shout out to Don Becker. That the work that he and Tom did in the early days was ratifying low-cost NE2000 drivers for Linux, right? So you could do Ethernet on the cheap. My big message, and whilst we've got Alan Benjamin here, is keep an eye on the costs of this stuff, because the reason why Composable is exciting right now is every server board comes with a PCI slot in it, right? And so we can all sort of see it. And we know we're going to need some gubbins around it to join them all together. But the cost of that technology is exciting because we see it as commodity. And so we see, as what Doug was saying earlier, we can do the wrong thing with it in a good way. And so I think that's going to be the thing in terms of the standards bodies for being able to compose between composable pieces. And it may well be that we can never do that. And that's okay too.
So let's pick up on that then, because let's observe that a lot of the story here is interconnects, right? If let's say you were to go out and buy a box of GPUs, one of the things the vendor will tell you is about their wonderful custom interconnect between the GPUs that you can use. And there seem to be incompatible things evolving. But you say, well, if I'm just going to stick all these things into a box that's got PCIe anyway, and if PCIe is getting faster, and if you look at what is the core of the Intel and even AMD product lines here, I'm less confident about NVIDIA, you realize that CXL is built in there anyway. That's how they're doing it. So maybe you say, I don't need all these fancy interconnects. Maybe I could just not buy as many things and work on extending the PCIe bus. So with that in mind, what's the roadmap for adoption of CXL 1 and 2 in the composable infrastructure product line? Is this guaranteed, or is it just an option? Or are we stuck with these vendor-specific ways of connecting multiple units together, which, by the way, only works for GPUs?
Well, I hope that, this one of the real strengths of PCI is the fact that so many companies, the PCI SIG has been strong, and we've seen an interesting one of the foundations for us. We have this disaggregated box, and it has the ability to plug PCI devices into this box. And there's almost nothing that we have plugged into that box that if they have been compliant to the PCI SIG has not worked. And we've plugged lots of things into this box. And it is, that's a tremendous strength. And so to the degree that, companies will invent their own interconnect, I think hurts them. If the world wants to go to heterogeneous computing and they want to take advantage of all those accelerators, I think in the long run, being on an island is going to hurt them.
Okay, Maria, James, anything to add to that? Or I'd like to leave enough time for the last question, but go ahead and answer.
I'll say something quickly. So I think CXL is needed to disaggregate DRAM. Right now, it's just not been done. And that's very interesting for the application perspective because of the finer granularity that will enable perhaps even at the cache line through load and store access. So that can open a lot of perspectives for improving application performance.
Great.
I'll just add, we need our NE 2000 moment, and then that's when it'll go gangbusters.
All right. Okay, so I'll take a moderator's privilege of answering this last question myself first. But the question is, what makes you most excited about the current state of composable computing or its future directions? I'm excited about not having to sit there and puzzle over any given researcher who wants to buy into our GPUs, how much memory to have to talk them into buying and what CPU choices, when I know very well I really want them to put this into a pool of similar machines so that we can do fair share queuing. I hate having to try to specify with each box which CPU, which amount of memory, which IO interfaces and all this. I like the idea of just saying, we're going to make a general resource and different workloads will use these resources differently. So Maria, what makes you most excited about the current state of composable computing or its future directions?
Well, I already talked about the energy aspect, so I won't repeat it, but that's my main one. But after that, the application gains that can be made through this. So how can the application benefit from a more flexible and abundant targeted allocation of resources? We know applications and workloads have phases. So how about we can bring the compute elements to the data, and so the application can work like that. That will save energy because you avoid data movement. Take the AI workflow, for instance, where you ingest the data, do the training, do the inference, and if you allocate the right number of resources for the right in the right amount to the phase, I think there are important performance gains that we can have.
Thanks, Maria. I'm with Alan there. I used to write the checks to the faculty for their special little computer that they lived in their box, and everyone wanted dedicated shared, which meant basically my computer, get off. And so the other problem with faculty members and research programs is they turn over, they go to new places, the center director's left with all this tin, they maybe try and repurpose it. And the second point that's really important is it's wasteful. And so I want to see a future where we can reuse equipment, repurpose it. There's the energy that goes into manufacturing a computer is vast. We tend to still really throw them away. We try. And I want to see an ability to be able to buy lumps of kit that you can easily be able to make new pods, not cloudy, user doing it. I'm talking admins that can carefully build systems for purpose, and then maybe use an orchestration engine into those pods. But if I wanted a machine with, 2 terabytes of RAM, do I need to go buy a 2 terabyte RAM machine? Because most of its interpreted languages, we're not talking about performance. We're just trying to get the job done and make it fit so it doesn't swap out to disk, right? So you're already winning on performance anyway. So,
right, so
that's the future I see.
This is in fact one of the sales pitches that you'll see out there is cloud-like flexibility in a box. Now, we've explored many of the limitations to this idea, but certainly that's one of the attractions is not just flexibility but performant flexibility. Let me just observe that, and before giving Alan the last word here, that in every level of computer science, we always choose worse efficiency in order to get better abstraction. So, that's, you mentioned interpreted languages. So, we always do it. We no longer program in machine language, and probably very few of us want to go back. So I've been observing the trend into the cloud as one of enormous inefficiency, and I'm going to claw some of that performance back. So Alan, Benjamin, I'm going to give you the last couple of minutes here to the question, what makes you most excited about the current state of composable computing or its future directions?
Well, I won't repeat what James and Maria said, and I think what they've said is absolutely fantastic. And I'll throw in, maybe one element is that it in an efficient structure where you have composable capability, it gives people an opportunity to experiment with new things without having to take a lot of risk and without having to spend a lot of money. So as an example, one of the exciting parts that we were working with the folks at San Diego Supercomputer was that they wanted to experiment with being able to use FPGAs for certain kinds of compute as opposed to GPUs. And normally that would have implied they were going to have to go buy a bunch of servers and other things. And because they had one of our systems there, they were able to take out some of the GPUs and simply plug in some of the FPGAs. Now they had to go buy the FPGA boards, but it gave them an opportunity to be able to experiment on, in a much lower cost way than otherwise. And so it breeds innovation.
Great. So I do see a couple of notes in the chat. Let's just very quickly mention that Dan Ernst points out less over provisioning is less silicon and less cost. The message I was reading from Dan Stanzioni are against that. If you buy a bunch of servers and you have to buy a bunch of external PCIe fabric, doesn't that drive your cost up? Well, I will send you to the vendors' websites to explore their answers to that question. But my summary is, it depends on what you're doing, but if you know what you're doing, you can lower cost. Mike Sherman says, my day job is making academic computing more reusable and accessible. ChameleonCloud.org, which I've used a lot, is a wonderful test resource if anyone wants to talk further on the topic. The breakouts are just about to end. So I will see you guys all back in the main session. And thank you so much for everybody's contribution. Maria, James, Alan, really well done. Thank you.